All right, I guess I'll get started. What I'm going to talk about today is mass production of meta-optics in a visible and near infrared um, using NIL patterning. Um, Start out with Moxtek. Full background on Moxtek. We are headquartered in Orem, Utah. We have two main divisions, X-ray division and optics division. We're a high volume manufacturer. We manufacture many thousands of wafers per year. We have clean rooms where we manufacture. Our optics fabs are in these buildings with quite a lot of clean room space. And we manufacture optics devices on a nanoscale. So our main product for many years has been polarizers, nanoscale polarizers, wire grid polarizers. So these little lines here are probably about 100 pitch and about a little less than 50 nanometers wide. So, oops, hit the button. So that was our main product for many years, and just recently we started manufacturing metal lenses and metasurfaces. This was enabled by we acquired a nanoimprint solution from Skill. And installed that, got it running. We brought it up on running wire grid polarizers and qualified it for production. And then we started looking at other products we could start making. So as you can see in this little graphic, most of our polarizers go into these projection systems. But then we started looking at other applications we could start getting into with the metasurfaces. So I'm not sure how many people are familiar with metasurfaces, so I'll kind of do a little bit of background. Basically, it's a flat lens similar to a Fresnel lens, where you build these meta atoms in different CDs, as the different CDs will propagate the wave front differently. Basically, you need a 2 pi phase wrapping to make a full lens. Most of our design work is done with RCWA. I guess a little background is we do design some of them ourselves, or we take customer designs and manufacture them because our main focus is manufacturing. The advantages of metal lenses are the size to weight is the #1 advantage. As you can see, like a conventional lens, even a micro lens is still rather big. You compare that to a metal lens where all the lensing function can be on this single layer, and the actual surface of the meta atoms is usually a micron or less. But another advantage is you can reach really high NA with these metal lenses. Also, you can do specific polarization sensitivity or aberration correction or other kinds of application specific things other than just imaging with these lenses. Well, you can design your metasurface to do a number of different things. Anyway, there's some challenges with bringing in metal lenses. It's kind of a new technology to bring to manufacturing. So the chromatic aberrations is #1 for the challenges. And some people are looking at a lot of different ways to do it. Some people are doing lens arrays and different things like that. The efficiency is not as good as conventional lenses, but that's improving in better designs and better manufacturing. But one of the big benefits is you can make these in high volume. So this is an example of one of our production replicated wafers. There's over 1,000 lenses on this 8-inch wafer here. Anyway, you can do that in high volume, so you can make a lot of lenses with just a few wafers. Anyway, so the basic objectives I'm trying to get by on this talk here is nanoimprint is really the key enabling technology to make meta optics in volume for the visible range. There has been some products released in the near IR using typical semiconductor processing lithography. But to get to the visible, you got to get a smaller wavelength, smaller meta-atom, and so then you need NIL. So then we've established a volume manufacturing production line for the visible with greater than 90% efficiency. And then we've started gathering statistical data sets on the MTF and volume runs of these visible lenses. But anyway, here's like 4 main points in making a visible meta optic. Like I was sort of mentioning, you need smaller dimensions to make the visible range. So this is a graph of the pitch at the binary limit of these meta optics, the pitches of your meta atoms to get the NAs you need. And you can see these different curves are like, this is near IR, and as you're coming down here, and then these curves in here, you're getting into the visible. And to get into the visible, you got to get down here pretty small pitches and pretty small structures to be able to make these optics. And right around this level is about where you're going to run into your limit for your typical semiconductor optical litho devices or systems. So here's kind of an example of a layout of a meta device. You're going to have large structures next to small structures, and these large structures have very tight gaps, and these small structures have very wide gaps, and that's where it sort of gets into problems when you're trying to do optical litho. So there's been some research to say that, you know, they're starting to figure out how to get some of these optical litho systems to make visible meta atoms. But the problem is, so this is like an example of a pretty good deep UV optical litho system you'd use in semiconductor manufacturing. But anyway, you have to have these spaces too far to make this work, or else they'll bridge. And what happens is you get zero order leakage. So if you got a lens that you're focusing and you defocus the lens, you'll still see a bright dot in the center where a lot of the zero order leakage is coming through. And the basic concept in making these meta surfaces is you want to fit a phase profile. And so as your phase profile is changing, if you have larger sections of it, you're going to lose some efficiency and some resolution. But then if you can make these smaller ones, you can fit it a lot better. And anyway, here's an example of an easily resolvable meta surface that has it's done by NIL. So it comes down to being able to pattern these little tiny structures. So here's kind of the landscape on what patterning looks like. So these are like your typical semiconductor optical litho pattern stations, and they get better as they go along. And this is like your high end, right before you get to EUV, and these are the kind of gaps you can be able to reproduce between your meta atoms. And then if you use like an E-beam master with NIL, you can get down into these little tiny gaps. And then this guy, as I kind of represent here, your zero order leakage is going to decrease and increase till you can get down into these very small structures. And all these others, I've been able to pull references out of current research to verify these. And then you get comparison of what the cost is going to be. So these older ones, they don't cost as much. This high end, I mean, this isn't even the most advanced and not the most expensive one, but it's very expensive, and you're still not getting to what you need. Anyway, E-beam is make the master, and then NIL for the volume production is really what we're going to need for visible metastructures. And here's kind of a bigger representation of a similar layout where the high-end optical cannot resolve these. These will be bridged if you expose it enough, so these aren't bridged. These small pillars go away. So that's kind of the problem. Anyway, to establish our high volume process baseline, we used a beam diffraction grading, so that it's very easy to tell the efficiency of our optics. So this is kind of a repeated grading, and it diffracts at a set angle. And so it's really easy to tell how much light is actually getting diffracted at that angle compared to what's being leaked through zero order or other orders. And we typically used a 5-site map across an 8-inch wafer, 5 sites per wafer, several wafers per lot, several lots, multiple masters even. And over some number of learning cycles, we were able to improve our efficiency up here to about a 90% baseline. So you can see early on, we're trying to figure out, what's going on, and we did some improvements. We were able to get it up here running around 90%, which is pretty good for meta lenses. So the big picture, trying to make a high volume meta lens production line, is you start out and you look at all the different research they have out there, and you're trying to figure out, what's going on, what are the new discoveries, and how are they making it? And then you got to figure out, well, what is the high index material we need to use to make our meta atoms? So here at Moxtek, we've selected niobium oxide. Has a high refractive index and low extinction. Anyway, then the next step is, what possible structures can you make from this stuff? So then we did a lot of test structures where we're making really tiny pillars with really small gaps. These pillars are actually 57 nanometers wide or somewhere in that neighborhood, and the gaps are even narrower than about 40. And then once you can build a process to make these structures, then you got to design visible meta devices. So we have an in-house design team that designed up some nice structures. And then we put on a 8-inch master. And then we want to do volume, so we want to make sure we fill up that whole master. And then we started running our process until we were able to make enough improvements and get it up to a baseline of 80%. So here's kind of an overview of meta lens manufacturing. You got to evaluate the designs, make sure you can build it. Engineers can design up whatever, but you got to be able to make sure you can build it into your process flow. So we kind of have a set of design rules of the different materials that we can use, or the different dimensions, and they're all on 200 millimeter wafers and the different substrates we can make. We start out, as you saw in the pictures, with rounded pillars, but we're working on lots of other different shapes too. Then you got to build your master, and to build your master, you got to take into account all the biases through your process to your final CD. So then you got to back calculate to make sure your master bias is set, so your final CD is as designed. You can see a lot of the work we did here is building a good master, and this is on a nanometer scale. So this is the bias plot on this scale, and this is the design CD plot on this scale. So you can see these are different devices, each line, but just in one of these lines is plus or minus just a couple nanometers on the bias that we were able to achieve. But when you start going into the process, you can see that the master is pretty tight. After our patterning with our NIL post-print, it stays nice and consistent. We lose a little bit for shrinkage, and then post-etch we get a little bit more variation, but it's still right in line. So we were able to make some good devices. This is an example of one of the ones we've made the 90% out of. So then you got to build this in a high refractive index. As I said, we use niobium oxide. At this step is where the height of your pillar is set. And then you take your process control and make sure you're on target for this. And then you got to pattern these. With nanoimprint, you can pattern many hundreds or thousands of wafers. But this one, you can see print 5 to print 134. They're, from the AFM scan, look identical, very close on the measurements. So I know this is sort of subjective, depending on probe tip and where you set the measurements, but they're still really close. And then this is an example, like I said, we did line spaces for a long time. So this is a line space SPC chart. So you can see we got many thousands of data points on it. So then you got to build your meta atom into your high refractive index material. So then you got to go through the etch, and you can see in some of these, this is post-etch SEMs, where we're getting a CD of down, just under 60 nanometers, an aspect ratio of over 13. And this gap in here is 30 nanometers. And this is one of the devices that was greater than 90% efficiency. But here's a little graphic of what you need to make all the different process parameters you need to achieve to make a meta device. And one thing to note is flat tops. So we combine, we take off our mask material and then we have flat tops. But anyway, you approach a 90-degree, you got these minimum spaces, you got varying sizes, and you try to get an aspect ratio of 12 or above. And then we have a number of post processes that we can incorporate. Over the years of making optical devices, we've learned quite a few things, and we can add these to our metasurfaces. And this is one where we can protect those tiny little structures. So with these two graphics, you can see we have an overcoat we put on here. And then if you rub it with a paintbrush, this one here is completely protected. But if you don't have any overcoat on it, you're going to destroy all those little tiny, just by slightly touching it. And then we can stack devices. So this is a wire grid polarizer with a metal end stacked on top of it. One point to note is if these are stacked within the sub-wavelength range, they almost act, they act like they're part of one device. But some people stack metal lenses where they're in separate devices, so they have independent functions. And then color filters, that's just another one we can throw on. So then the next thing I was going to talk about is our performance measure, and those are measured in efficiency and MTF. So this is just a little background on what MTF is. It's basically your resolution on your line space and how clear your resolution is you can make clear. So then each lens is going to have a theoretical optimum MTF, and then you're going to have some sort of deviation on what your lens is actually making. And so I'm going to show some data on this. So this is kind of an interesting thing we found. As I mentioned before, efficiency on these meta lenses is kind of important. So if you got a couple different designs, we have a standard design, which you see in most of the literature, and then we've come up with a better design. Anyway, the MTFs are pretty close between the two designs, but the efficiency is way different. So efficiency is important. So one of the key takeaways is even if you can get a good good clear MTF, you can lose a lot in different reflections for a poor design. Anyway, this is a 1 millimeter diameter lens at 532 wavelength. This data set's from 37 wafers and so on. Anyway, we have test, and in the same 5 sites, we have a test lens kit with 12 different lenses. Here's a variety of lenses, and you can see the MTF, and these are all like 38 wafer data set. Anyway, this is a good example of process control inline. So we have an inline process control. I didn't really sort of mention it in the imprint step, but anyway, we saw a problem with our post print SPC. We made a process change, and then we brought our MTF right in line. You can see that it works pretty good. And then here's our 49 site. We have a production wafer. I showed that earlier. I had 49 site MTF, and this is all within a few percent of the MTF across the whole wafer. We had a few sites on the edge that dropped off, probably processing problems. And then we took these meta lenses and compared them to conventional lenses. So this red MTF line is our meta lens, and the blue is the conventional lens. And this is just a conventional lens we pulled right off of Edmunds. But here's an example of what the size difference of the lenses. So here's your conventional lens. This is a blue line, and then here's our meta lens. That would be the red line, right? And this is 1,000 times thinner, but still performing the same or better. Then this is a lens. We didn't actually measure this one, but this one's off Edmunds. The specs are off Edmunds of a focusing lens. And so we compared it to a matching meta lens that we built. And you see, this is our line for MTF. And this is their line for MTF. And this huge compared to about 1 micron's worth of metal atoms on top of this substrate here. will get you your same impact. So anyway, here's a number of different lenses we've built, different diameters, different operating wavelengths, number of different focal lengths. Tested all these from multiple wafers, several, got a pretty good sample size of a lot of these. And then we made this over the last year for trade shows. We made this demo where we put one of our metal lenses on top of an iPhone camera. And basically, it changes the focal length and then makes it more like a magnifying lens. So the point of this is you can see all the different colors, and they're focusing quite well with this metal lens on here. Anyway, just to put it in a real world application so people can actually hold it in their hands and see what how it works. But back to my conclusion. So hopefully I showed and convinced you that NIL is going to be the key technology to go for visible metal lens production. We've done the work here to establish a good baseline on our production line of better 90% total efficiency. And then we're building quite a few metal lenses and a good statistical database on MTF and can compare all those things. And the basic point is that metal lenses, the form fit is thousands of times thinner than a conventional lens and can fit into a lot of different applications. So that's all I had. I guess if you want more information, you can scan this QR code and get to our website, or you can email me directly. I know there's not a trade show at this conference, but we have some throughout the year. And if you're ever at one of those trade shows, come by and take a look at our demo setup, and you can see metal lenses in action, visible metal lenses in action, I guess. Anyway, I guess if we have time for questions, I did pay attention to the time.